This is the video for IB Chemistry Unit 2, Notes A, about the atom. We're going to go through a little bit of the history of the atom, but you'll notice in the following slides that some of them have a bit of a beige background. Those are not on the note takers themselves, it's just kind of giving you a historical context. And then the ones with the white background will be the ones that follow the note takers in order that you found in the packet. So a few basic principles about the atom should be mostly reviewed here. There are three basic subatomic particles: protons, neutrons, and electrons. Protons and neutrons, of course, being found in the nucleus, and the electrons surrounding the outside in layers. We've talked about energy levels or shells, where the electrons orbit around the nucleus. It does mention here that hydrogen is an exception, and that's because hydrogen actually has an atomic number of 1. So that would mean 1 proton, and then its mass number is also 1. So 1 proton, 0 neutron. So it's the only atom that we know of that does not have a neutron. It just has 1 proton and 1 electron. The atomic radius, or the distance between the nucleus and one side, so think half of a circle, right? The radius is very small. Of course, atoms are very small. They should say 10 to the negative 10th. So that's about the size of an atom, just to give you kind of an idea, a base point. And then the next point here is that atoms are made of mostly empty space. So all of these layers out here, the electron shells, they're all made of electrons. Well, all electrons are negative, and what do we know about things with like charges? They're going to repel. So basically, the entire space that the atom is being made of is just the area in between electrons that are pushing away from each other. So what you end up with is a whole lot of nothing, just kind of scattered around with some electrons. This is very similar to when we talked about gases. We talk about the density of a gas. You have a couple of particles, but the bulk of the actual volume is the empty space between the particles. Last point here. Well, okay, so protons and neutrons located in the nucleus. You should, of course, know that by now. And then the last point here is that electrons are found in energy levels or shells. So towards the end of Unit 2, we're going to go back to electron configurations and talk about the movement between these specific shells or energy levels. We're actually this time going to calculate how much energy an electron would have in certain levels and how much it loses during a transition. So that's kind of where we're going with this. All right, so this is essentially the slide that we started the concept of an atom with in honors chemistry. You learned that Democritus was the person who very first thought of an atom, and learned that the word atom actually comes from the Greek word atomos, which means indivisible. So he was a philosopher, not so much a scientist, philosopher, meaning he had these ideas. He didn't necessarily conduct experiments. So his idea ties to the science because the idea was about how something at its base point is unique and indivisible. So that applies to atoms in the sense that if I take carbon and I cut it down to the smallest particle of carbon that is unique, that has specific physical properties, it has a melting point, it has a phase, it's solid at room temperature, it has unique identifying characteristics. As opposed to maybe argon. Argon is a gas at room temperature. It is inert or non-reactive. It has different physical properties, would have a different melting point, things like that. So that makes those two atoms different. Now in 420 BC or approximately then, because who knows, right? They didn't necessarily call it carbon and argon, but maybe they said, okay, a rock, the smallest piece of a rock at some point has an identifying characteristic and is different than the water in that pond. So that has a completely different set of properties than the rock. The rock's a solid, the water is a liquid. They have different characteristics. So let's call that a rock atom and a water atom, or atomos. So that's kind of the idea. And we learned that this came from Greece, from this guy, Democritus. But do you really think that all people around the world learn the exact same facts? Or is there something that they call a bias? Something that the way we learn is a little bit different from the way that they might learn in Europe or Australia or China. So I'm having some technical difficulties on importing this slide into my recording software. This quotation box doesn't actually belong there. So first let me read you the slide and then we'll talk about it. The slide is posted, the PowerPoint is posted if you want to see the unaltered PowerPoint. So first point should say, many historians believe the idea was first proposed at least a century earlier in the Indian subcontinent. And then the second point says, the theory of atomism was also much developed in both Chinese and Arabic cultures during the Dark Ages in Europe, when many of the teachings of the church dictated much of Western thought. So we talked a little bit about the gap in scientific development. So there's 400 BC was when we talked about Democritus first having this idea of an atom. And then John Dalton's theory happens in the 1800s. So why this big gap? Well, as they're talking about in this point here, we had a lot of problems. We had the plague and all kinds of actual health issues. We had an era of artistic and religious development. So that kind of stopped scientific development in the Western culture. But the idea here is, okay, so what about the Eastern culture? Did they grind to a stop as well? Did the same plague affect them? The Black Plague was mostly in Europe, so why would China, for example, be as impacted? It just doesn't make sense that all cultures would have the same exact experiences. So the idea here is just to kind of open your mind to the thoughts that there may be different theories. We went over some of the big players for our culture, but there are other important scientists out there that we'll talk about their ideas as well now, because we are in the international baccalaureate program. So let's tie this back to the theory that we discussed, which was John Dalton's theory. Again, we're already in the 1800s here. He described how atoms should behave. So although we still didn't necessarily have everything named, we may not have every element identified, he's still starting to describe or explain what an atom really is, a little bit more than just the thought in 400 BC of, hey, that rock is different from that water. So the first postulate is that all elements are made of tiny atoms. So this sets the precedence that atoms are the building blocks of molecules. It also says atoms cannot be subdivided. Well, that's kind of true, but they can be divided into protons, neutrons, and electrons. However, if you do go that small, you lose the physical properties. So they can't be subdivided without losing its identity or its physical properties. Atoms of the same element are exactly alike. Postulate 3, maybe not exactly, because we have ions and isotopes. But what you can say is that they have the same atomic number or number of protons. And then the last one, atoms of different elements can join to form molecules. And that ties back to the first one where atoms are the building blocks. However, it doesn't necessarily have to be different elements because you have diatomic elements as well. So that would be the same element joining together. We would still call this a molecule. So now that we've thought of atoms, now that we've identified about what makes them an atom, idea of atoms, now we start multiple places to get we've explained a little bit about atom, and the very first subatomic particle discovered would be from what was the first subatomic particle? They did this experiment that would be together. The electron. So there's actually something called the Plum Pudding model. That's an atom. So what happens is a little electrons are just floating around inside of the atom. They don't know about the nucleus. They don't know about levels. They just think that these electrons are floating around in there. I guess plum pudding would be something along the lines of throwing chocolate chips in a bunch of cookie dough, and they would just be scattered about haphazardly, just thrown through there. So I guess plum pudding was more of the times. But think chocolate chips and cookie dough, they're just kind of there. the experiment that they used for this, the most famous part of it was the cathode ray tube. So cathode and anode may be familiar terms from redox when we talked about how a battery worked. So basically this is using opposite charges, trying to see how the electrons would react. Electrons coming close to the positive end would be attracted and negative end would be repelled, and so you see this effect of magnetism that you're able to watch. The name of the entire experiment, by the way, was the oil drop experiment. But the actual tube structure, the cathode ray tube, is what made them famous. Probably one of the most well-known guys related to the atomic development would be Rutherford. So Rutherford is known for finding the positively charged nucleus. Some people say that he found the protons or neutrons, which is actually wrong. There was a lot of people involved in discovering those actual subatomic particles. But he's the first one that realized that, hey, there's not just a bunch of electrons floating around, that there has to actually be a positive center. So his super famous, of all the experiments, you should know this one, super famous experiment is called the gold foil experiment. So here's the gold foil. He would blast alpha particles through them, which you may recall from nuclear chem is a helium nucleus. So basically it's 2 positive charges, no negative charges, and 2 neutrons. So very positive particles being shot through, and then there was deflection. Why would there be deflection if there was just a sea of electrons in the middle? There must have been something positive in the middle. So this deflection from their path is actually what led him to conclude that there must be a positive center in the atom. So now we're going to talk about the mass and charge of protons, neutrons, and electrons. And keep in mind that the most important takeaway from this is that it is all relative. So they have actually developed a unit called atomic mass unit. They have a way of describing how one charge relates to another charge. So this table that we see here basically is helping us understand the ratios. But there are exact numbers given, and they are given in the IB booklet that you would use on your IB exam. And then keep in mind our online test that we're taking due to the quarantine is going to be open note as well, so you would have these numbers given. So it's not that you have to memorize these numbers, it's that you need to appreciate the relationship between the mass of one thing to a mass of another thing, or the charge of one thing compared to the charge of another thing. So looking at mass first, the mass of an actual proton is 1.672 times 10 to the negative 24th grams. That should be a superscript. But we always say, like in relation to the atomic number or mass number, that that's just a 1. So what that actually is a translation to the relative mass. The mass of a proton is exactly equal to the mass of a neutron. So when we say the mass number is 4, but we have an atomic number of 2, well, 2 protons would equal the mass of 2 neutrons, and that would add up to 4. So that's how we know that we have 2 protons and 2 neutrons, if we have a mass number of 4 and an atomic number of 2, like with helium. So it's kind of identified by its relationship. An electron is much smaller. It is 1/2000th of this mass. So in relation to if a proton was a mass of 1, an electron would be 5 times 10 to the negative 24th. Again, that should be an exponent to the negative 24th. So it's very, very small. So it does not weigh in on the atomic mass at all, or the average atomic mass, relative molar mass. It does not affect those masses. It does have a mass because it is matter. It is matter, not energy in that sense. But it is such a small mass, we would almost consider it negligible, or we would consider it negligible in context of calculating something like the molar mass. I've used the example before. If you are trying to lose weight and you pull a hair on your head and you step on the scale, would you really expect to see a change? Of course not. That's kind of the analogy of removing one electron from an entire atom, it is not going to notice a change in mass for losing or gaining 1, 2, 3, any type of, or any amount of electrons is not going to change the relative mass of the particle or the molar mass of the particle. Looking at charge, there is actually a measure of charge. You may have heard of this in physics. The unit for that is called coulombs. And that registers basically the attractive force between particles. So for the charge of an electron, it is 1.602 times 10 to the negative 19th. Again, that should be an exponent. And that charge for a proton is the exact same number but opposite charge for an electron. A neutron, however, does not have any attractions between particles, so you see its relative charge being 0. Just wanted to do a quick review here. This is basically what a block on the periodic table would look like. The atomic number is going to be a whole number written at the top. The element symbol will be given. Sometimes, not usually in an upper level course, but sometimes you may also see the element's name right under the symbol. And then you'll always see an atomic mass with a decimal given at the very bottom. And we're actually going to talk a lot about isotopes this unit and why that is a decimal. Just wanted to review real quick how to count up how many protons, neutrons, and electrons there are based on these numbers. So the number of protons is always going to equal the atomic number. So if the atomic number is 6, that means I have 6 protons. If I do not have an ion, notice how it says it's in a neutral atom, then the number of protons equals the number of electrons. If you do have an ion, if it's positive, you have that many less electrons, and if it's negative, you have that many more electrons. And I know that may seem a little bit opposite, but keep in mind electrons are negative. So if I had an oxygen with a 2- charge, that would indicate I have 2 extra electrons. So whereas I would normally have 8 electrons, 2- would have 10 electrons. If I had a hydrogen ion, where it would normally have 1 electron, 1 proton, 1 electron, if I have that H+ ion, it's literally only a protein. It loses that 1 electron. So positive charge means less electrons, and negative charge means more electrons. To get the number of neutrons, you're going to round your atomic mass. So 12.011 would be 12, and then subtract the number of protons, or the atomic number. So 12 minus 6 is 6 neutrons. So this would have 6 protons, 6 electrons, and 6 neutrons for carbon, for regular carbon-12 atom. So this is a very common format. They call it shorthand notation in IV for an atom or an ion. You take your chemical symbol. This is always going to be the symbol, not the name. So like C, not carbon. And then in the top, you always put your mass number, and in the bottom, you'll put your atomic number. And again, the mass number is protons and neutrons, whereas the atomic number is just the protons. And if you subtract those, you can get the neutrons. So mass number up top, atomic number on the bottom. And then on the right of the symbol, you would put the charge up to the top. +2, -2, 3-, 2-. It doesn't actually matter whether you put the number or the plus or minus first or second. They are interchangeable. I've seen it both ways a million times. So you just put like what the charge is up there, and then that's going to affect your number of electrons. So normally protons equal electrons, but if you see a minus, then it's going to have more electrons, and if you see a plus, then it would have less, just like we just talked about. So that's where you're going to find kind of the directions on whether to have extra or less electrons. There is actually a use for this bottom area here. That's where you would put a subscript, meaning basically it's the count of the atoms. So you're not going to see that on lone atoms, but that is a special spot designated for subscripts. All right, so I know you can already see all the answers, but we're going to talk through these three examples. You might want to pause the video and try to fill out the chart in your note takers without looking at this slide, and then hit play on the slide to check your answers. So starting with 9 for B. So the atomic number is always going to be on the bottom, so that's the 4. The mass number will always be on the top, so that's the 9. The number of protons is the same as the atomic number, so again 4. For the number of neutrons, you're going to take your mass number of 9 and subtract the 4, which is 5. And then there's no charge on this one, so the number of protons is going to be equal to the number of electrons. All right, looking at the next one, the 4020 calcium, but it is an ion. So the atomic number again is the bottom number, which is 20, and the mass number is the top number, which is 40. Protons are going to be equal to the atomic number, so again 20. And for the neutrons, we're going to take our mass number of 40 and subtract the atomic number of 20, which is also 20. This one does have a charge. So normally protons equal electrons. So the protons were 20, so I would expect 20 electrons. However, this has a 2 plus charge, which means 2 less electrons, which is 18. So we have 18 electrons. Okay, last one, the 3717 chlorine ion. So the atomic number on the bottom is 17, and the mass number is the 37 on the top. The number of protons equals the number, or the atomic number, so 1717. And then the number of neutrons is going to be the mass number 37 minus the atomic number 17, which is 20. So normally the protons equal the number of electrons. So if the number of protons was 17, you would expect that there would be 17 electrons. However, the negative sign means I have one more electron. So plus 1 is 18. So this one actually also has 18 electrons. So next we're going to go over hydrogen, carbon, and chlorine, and the very common isotopes of those three atoms. This is just presented as examples of isotopes, but I've got to tell you, these are really, really important to know. You should know what the most common isotopes of these three elements are. They will come up over and over again. So I think, personally, I would recommend that these are worth memorizing. So for hydrogen, the hydrogen 1 would have 1 proton and 1 electron, because 1 minus 1 is 0 neutrons. Deuterium, so the isotope with a mass number of 2 for hydrogen, would have a proton and electron, and then 2 minus 1 actually gives me also 1 neutron. And then there's also an isotope that has a mass number of 3 for hydrogen, and so you've got a proton, an electron, and 2 neutrons. So yes, there are other isotopes of carbons. Carbon is actually one of the most complicated atoms on the periodic table, but these two forms absolutely by far take up like 99% of all the isotopes in the world of carbon. So carbon 12 is what we usually deal with in orgo or organic chemistry. Carbon 14, however, we're actually going to talk about again later in this unit. It's used for radioactivity because it can be used for something called carbon dating. So maybe you've heard of, or actually I think in honors we talk about how carbon can be used to figure out how old some organic molecules are, because there's something called the carbon cycle, which you may have talked about in biology. So we're going to see all this come together when we talk a lot more about the isotopes of carbon in the next set of notes. But for now, you should know that there are two main isotopes of carbon. One's carbon-12 and one's carbon-14. So carbon-12 is going to have an atomic number of 6, so 6 protons, no charge here, so also 6 electrons. And then for the neutrons, 12 minus 6 is also 6. The radioactive or non-stable carbon would have also 6 protons, 6 electrons, but 14 minus 6 actually gives 8 neutrons. So that wrong neutron number is what makes it unstable and useful for carbon dating because it's radioactive. All right, so the last set of isotopes are for chlorine. And I know chlorine may not stand out to you on the periodic table right now. No particular reason you should know it. Of course, carbon and hydrogen have come up a lot, maybe not so much chlorine. But in my experience, chlorine comes up a lot in IB sample exams, and I've seen it on old IB exams quite a few times. It's kind of one of their tried and true go-to questions. They usually ask it when they're talking about isotope questions. So I think, my 2 cents, I would memorize that there are 2 isotopes for chlorine, chlorine-35 and chlorine-37. I think that will come in handy if you're taking a chem exam. So to break this down, chlorine-35, chlorine has an atomic number of 17, so you see 17 protons, no charge, so 17 electrons, and you see that for both of them. For chlorine-35, 35 minus 17 gives 18 neutrons, and 37 minus 17 gives 20 neutrons. So those are your main 2 isotopes. So the first thing that I want to point out here is that the question asks you to find the weighted mean molar mass. So I want to talk a little bit about what the weighted mean means before we get into the actual calculation with molar masses. So weighted mean just basically means a weighted average, which is exactly what we do for your grades, like in Q. So mean, if you think back to mean, median, mode, literally is what we usually call an average. So you take 10 numbers that go into a category, you divide it by 10, that's your average. That's exactly what we do when we do average of 3 trials. Take your 3 final answers, add them up, divide them by 3. That's how you get your average for your lab reports, right? So we're just finding basically an average, but making it weighted means that we apply category weights to them. So say test count for 50% of your grade. You would take 0.50, and then say your test average, again just a normal average, is a 90. So I'm going to take 0.5 times the 90. And then say homework is the other 50% of your grade. So I'm going to take another 0.5. But say you never do your homework and you have a 20% in your homework. That would then add all up to your final grade in the class. That's a calculation I know you guys are familiar with. Now we're just going to do it by taking the percentages of isotopes times the masses of the isotopes to give us the weighted average mass. So let's look at this example. So it points out the 2 isotopes of chlorine, and we just talked about these. Chlorine-30. So in this example, we start with chlorine-35 and chlorine-37. Again, like we pointed out when we looked at the isotopes, these are the main 2 isotopes of chlorine. So the question actually gives us the percent abundance. Key term there, percent abundance. So this says I have 75% chlorine 35 to 25% chlorine 37. So it's a 3-to-1 ratio basically. I have 3 times as much chlorine 35 as I have chlorine 37. But think of this as part of a whole, right? So if I had 100% chlorine, 75% of that would be the chlorine 35, but only 25% of that would be the chlorine 37. So I want to find the percentages of each mass and make them part of the whole. So what you're going to do is you're going to take your percentage, 75%, and you're going to multiply that by the 35 molar mass. You're going to take your percentage, 25 and multiply that by the 37 molar mass. So for this first part, you get 26.25. And for the second part, you get 9.25. So if you add 26.25 and 9.25, you get 35.5 exactly. Given the 2 sig figs in the problem though, if this were my IB test, I would give 36 gram mole -1. So this is a sneak peek of the calculations that I'm going to go over in my second video. I wanted to show you that relative abundance questions aren't always that I'm going to go over with you. This is isotopes. There's a way to read things off the graph. This is something that I have to go over by writing it out. So I'm going to make a different video in a different format to be able to go over a question like this with you. So please make sure you watch that video as well. Thank you.